You know, it's funny how we take something as basic as a number for granted in programming. But have you ever really stopped to think about what a floating point number is inside your computer? Well, today, we're going to tear a 32-bit float apart, piece by piece, using the IEEE 754 standard as our guide. And along the way, we're going to uncover a really bizarre and dangerous bug, a little something I call the signed zero trap.
So in our last explainer, we kind of looked at floating point numbers from a 30,000-foot view. But now it's time to get our hands dirty. We're going right under the hood to see exactly how a 32-bit float is put together bit by tiny bit.
When you write something like float x equals 3.14 in your code, it feels so simple, right? But that simplicity, it's really just an illusion. Down at the hardware level, that one number is actually this complex 32-bit package, and it's meticulously built from three very, very different parts.
So how in the world do we make sense of this structure? Well, the source material gives us this perfect analogy I love, the data sandwich. Let's take a look and see what ingredients make up these 32 bits.
Here they are, the three layers of our data sandwich. First up, you've got a single bit that just handles the sign, positive or negative. Next, there's an 8-bit chunk that controls the scale. We call this the exponent. And finally, the biggest part, 23 bits, defines the precision, or what we call the mantissa. Each piece has a very specific job.
Now these three parts aren't just stored next to each other. The hardware combines them using a very specific formula. The sign bit is like a switch that flips the number between positive and negative. The exponent sets the magnitude. Is this thing huge or is it tiny? And then the mantissa provides all the specific digits that give us the precision we need.
Okay, let's start with the simplest part of the sandwich, that little sign bit. It seems totally straightforward, but this one tiny bit is hiding a very, very strange quirk in the system.
So it all comes down to this one bit, bit 31. And it really just acts like a simple light switch. If it's 0, the number's positive. If it's a 1, the number's negative. That's it. This one bit controls the polarity for the whole shebang.
But this simple switch leads to a really fascinating question. What happens when the other two parts, the exponent and the mantissa, are just a sea of zeros? The value is obviously 0, but we can still flip that sign bit. What does that even mean?
And here is the bizarre result. In the world of integers, 0 is just 0. But in the floating point world, we get two of them. There's positive 0, with every single bit set to 0, and then there's negative 0, where the sign bit is flipped to 1, but everything else is still 0. Wild, right?
Okay, moving on. Let's look at the next ingredient, the exponent. This 8-bit section is what gives a number its scale, making it either absolutely huge or incredibly tiny.
But this creates a really clever engineering puzzle. See, the exponent has to be able to handle massive numbers, like 2 to the power of 50, and also tiny little fractions, like 2 to the power of negative 30. The problem? These 8 bits can only store positive whole numbers from 0 to 255. There's literally no room for a minus sign. So what do you do?
Well, the solution is just brilliant. Instead of trying to squeeze in a sign, the engineers just shifted the entire number line. They created what's called a bias. They basically decided that the stored value of 127 would represent an actual power of 0. So 127 became the new center of the universe. Anything stored above it is a positive power, and anything below it is a negative one.
And the process is just beautifully simple. To store a power, you just add 127. So, for an actual power of negative 3, you store 124. When the hardware needs to read it, it just subtracts 127 to get back to the real value of negative 3. It's a simple little offset trick, and it solves the problem perfectly.
All right, on to the final and the largest part of our data sandwich, the 23-bit mantissa. This is where the actual nitty-gritty precision of the number comes from.
The easiest way to think about the mantissa is that it's everything that comes after the binary point. You know how in decimal each step to the right divides by 10? Well, in binary it divides by 2. So the first bit is worth 1/2, the next is 1/4, then 1/8, and so on, with each bit's value getting cut in half as we move to the right.
So to figure out the final precision, the hardware just zips through these 23 bits from left to right. It starts with bit 22, which is worth 0.5, and it goes all the way down to a teeny tiny fraction at bit 0.
Then it just adds up the values for every single bit that's flipped on.
Okay, we've seen all three ingredients. Now, let's put our data sandwich back together and see how this very clever design actually creates a dangerous trap, a place where pure math collides with the physical reality of computer memory.
And this right here gets us to the absolute core of the problem. Mathematically, +0 and -0 are the exact same thing. But inside the computer's memory, they are two completely different bit patterns. And why? It's all because one of them starts with a 0 and the other one starts with a 1.
So, where does this actually become a nightmare? Well, imagine a physics engine in a video game. To check if an object has stopped moving, a programmer might be tempted to use a really low-level function like memcmp to do a raw bit-for-bit comparison between the object's velocity and the value 0.
But what if, through some calculation, the object's velocity ends up being -0? Well, that raw memory comparison is going to fail. The bits for -0 simply don't match the bits for +0. And so the game engine actually thinks the object is still moving, and it's all because of that one single sign bit.
And this is the result. The code literally rejects reality. Even though the object is mathematically at a dead stop, that memory comparison says, nope, they're not the same. So the code that's supposed to stop the object's physics calculations, it just never runs. The object is now stuck in this phantom moving state, maybe forever.
So what's the ultimate lesson here? It is so crucial for anyone working close to the hardware. You have to respect the raw bits. You got to remember that a float is a complex composite structure, not just a simple integer. And because of that, you should never, ever use raw memory comparisons on them. Always trust the math, not the bits.
It really makes you think, doesn't it? I mean, if a simple float is hiding all this complexity, what other simple data types have their own strange architectures and hidden traps waiting for us, right under our noses?
In our next explainer, we're going to continue down this rabbit hole. We'll explore the even weirder concepts of the ghost value and reserve values in the IEEE 754 standard. So stay tuned.